Hi students, welcome back. Today we are going to see third module of unit number 5th, that is passband digital transmission. Today we are going to study QPSK, that is quadrature phase shift keying. But before studying our today's topic, let's have a quick revision what we have studied in last lecture. In last lecture, we have studied BFSK, that is binary frequency shift keying. In that, frequency of your sinusoidal carrier wave, it is going to vary according to your binary symbol, that is 0 and 1. It means frequency of this sinusoidal carrier wave, it is going to vary in between two levels, that could be high and low level. Then we have seen the generation and detection of your BFSK. In detection, we have seen both coherent detection as well as non-coherent detection. And as you already knew, the difference between what is coherent and non-coherent detection. Basically, the demodulation in your non-coherent BFSK, it is going to take place with the help of what? Envelope detector. Then we have seen the geometrical representation of your BFSK. We have seen few drawbacks, applications of it. Then we have compared BFSK with BPSK. So almost when we have compared them, they are equal. Just the major difference is that bandwidth requirement of BFSK is much more than that of your BPSK. If BPSK it is going to take 2 FB bandwidth, then BFSK it is going to take 4 FB, that is 4 times of your FB bandwidth. It means basically BFSK it is suitable for low bitrate applications up to 1.2 kbps. So today we are going to study the generation and detection of your quadrature phase shift keying, that is QPSK. Then we are going to see signal space representation or geometrical representation of QPSK. Then the power spectrum of your coherent QPSK. Then what are the advantages and disadvantages of your QPSK? And at the last, we are going to compare QPSK with BPSK. So let's move towards our today's lecture, that is QPSK. The modulation that we have discussed so far, that is your BFSK and BPSK, are all what? Two-level modulations, because they are going to represent only two states of the digital data, that is 0 or 1. Hence, the bit rate and the baud rate are same for these systems. The maximum bit rate which can be achieved using your amplitude shift keying or your BFSK or BPSK systems, they are not going to meet the requirements of the data of communication system. This happens due to what? Limited bandwidth of your telephone voice channel. So we can keep this band rate same, but we are going to increase what? Bit rate by using which technique? That is multi-level modulation technique. In this type of system, the data groups are divided into groups of 2 or more bits, and each group of bits it is going to be represented by a specific value of your amplitude, or it could be frequency, or it could be phase of the carrier. So QPSK it is an example of such multi-level phase modulation. Now starting with QPSK. QPSK, that is your quadrature phase shift keying, the two successive bits in a bit stream are combined together to form a message, and each message is represented by a distinct value of the phase shift of the carrier. You can get the clear idea from this diagram. In this diagram, you would come to know that there are 4 symbols are there: S1, S2, S3 and S4. In S1, you can see since these two bits, that is 0, 0, they are going to form one pair. And this one pair, it is nothing but your symbol S1. Similarly, bit 0 and bit 1, they are going to form a pair of 0, 1, and they are called, it is called symbol 2, S2. Similarly, third bit, it is of this bit and this bit, they are going to combine to form a pair of 1, 0, and this symbol is represented by S3. And similarly, these two bits 1, 1, they are going to form a pair, that is a 1, 1, and it is represented by symbol S4. This is called symbols. These are called symbols, or we can also call it as what? Message. So it is a multi-level modulation. It means more than it is 2 bits, we are going to combine it. And you can see from this figure the duration of each bit, it is of duration what? TB. And similarly, each and every bit, it has a duration of what? It is of TB. So what is TS? It is a symbol time. This is going to be what? Twice of TB. That is a symbol duration, sorry. So this symbol duration, it is a addition of this TB plus this TB. That's why symbol duration TS is equal to what? Twice TB. So please remember, for QPSK, TS is equal to twice of TB. Now, the quadrature phase shift keying QPSK, it is a variation of what? BPSK. It is also called a double sideband suppressed carrier, that is DSBSC modulation scheme, which sends 2 bits of information at a time. That could be 0, 0, 0, 1, 1, 0, or 1, 1. So instead of conversion of these digital bits into series of digital stream, we are converting them into what? Bit pairs, which is going to decrease what? The data bit rate to half. And when this data bit rate, it is going to reduce, it is going to allow the space for others user also. This is the advantage of your QPSK. From this table, basically it is a way to represent your QPSK. So how? Now we are going to see. Now this is a phase shift in QPSK. This table, it is going to tell you that there are total 4 symbols are there: S1, S2, S3, and S4. And these are the input successive bits. Since each symbol, it is going to be consist of 2 bits, then S1, it is going to represent 0, 0, S2, 0, 1, S3, 1, 0, and S4, it is 1, 1. And this last column, it is going to tell you that when 0, 0, that is symbol S1, is transmitted, there is no phase shift in the carrier. That is, it is represented by what? 0 degree phase shift. But similarly, when symbol S2 is going to transmit, that is bits 0 and 1, then there is a phase shift in the carrier, which is of what? 90 degree with respect to your S1. Similarly, when we are going to transmit symbol S3, that is 1, 0 pair, then there is a phase shift in the carrier of what? 180 degree with respect to your S1. Then at the last, if you are going to transmit the symbol S4, then that is 1, 1, then there is a phase shift in the carrier of what? 270 degree. So you can represent this by means of this constellation diagram. So you can see that on x-axis, first it is your S1 symbol, that is 0, 0. Since S1 it is going to transmit, there is no phase shift. So that's why it is appeared on this x-axis. But similarly, when S2 it is going to transmit, you can see from this table that there is a 90 degree phase shift with respect to your S1. So the phase difference between your S2 and S1, it is of what? 90 degree. Similarly, when there is a transmission of bit the symbol S3, that is 10 pair, there is a phase shift of what? 180 degree with respect to your S1. And similarly, at the last, when you are going to transmit symbol S4, that is 11, then there is a phase shift of this 90 plus 90 plus 90, that is 270 degree with respect to S1. Now we are going to see the alternate way of representation of your QPSK. Now we have seen the phase shift, it is of what? 90 degree. Now in this table, the four symbols are common. S1, it is going to represent your 10 pair. S2, 00. S3, it is your 01. And S4, it is what? 11. So when we are going to transmit symbol S1, that is we are going to transmit 10 pair, then there is a phase shift in the carrier of pi by 4 radian or 45 degree with respect to your reference. After that, if I am going to transmit a symbol S2, that is 00, then there is a phase shift of what? 3 pi by 4 radian with respect to your reference. Similarly, when we are going to transmit S3, there is a transmission that is of 01 pair. It is going to tell you what? 5 pi by 4 phase shift in the carrier. And similarly, at the last, if you are going to transmit symbol S4, that is 11, there is a phase shift of 7 pi by 4 radian with respect to reference axis. So you can see this diagram that is called as constellation diagram of your QPSK. This axis we have taken it as a reference axis. So you can see from the table, if you are going to transmit S1, that is 10, then there is a phase shift of that which is going to be represented by phi is equal to what? Pi by 4 radian, or we can say 45 degree. Similarly, if you are going to transmit it S2, that is the 00, then there is a phase shift of what? 3 pi by 4 with respect to this reference axis. Similarly, if you are going to transmit this S3, then there is a phase shift of what? 5 pi by 4. And at the last, if you are going to transmit S4, that is 11, there is a phase shift of what? 7 pi by 4 radian. So this is your alternate way of representing your QPSK. So from this table, as we know that in BPSK equation we have written B of t root 2 ps cos omega ct. Since B of t, it is going to represent what? It is going to represent 0 or 1. That is plus 1 or minus 1. But over here, there are possible 4 symbols are there. So that's why we have made some modification in that equation, and we have written the equation for the QPSK, that is V QPSK t is equal to square root of 2 ps cos of omega ct plus 2m plus 1 pi by 4, because this is the integer multiple of your pi by 4 radian. So we have written pi by 4 as a common phase shift. So over here, m, it could be 0, it could be 1, it could be 2, it could be 3, because there are 4 possible symbols are there, S1 to S4. So if you are going to put m equal to 0, so you can get the equation. What equation you would get? Since it is a 0, then you would get the equation omega ct plus pi by 4. That is your symbol S1. But if you are going to put m equal to 1, then what you would get? You would get third phase shift, that is 3 pi by 4, that is S2 symbol. And if you are going to put m equal to 2, then over here you would get 5 pi by 4. That is symbol S3. And at the last, if you are going to put m equal to 3, then it would be what? 7 pi by 4. That is symbol S4. So this is the one of the most important equation, because now we are in this Next slide, we are going to use this equation for representing your QPSK. Please note down this equation. It is one of the most important equation. And what is PS? Now PS over here, in terms of symbol energy and symbol time duration, if I want to represent this PS in terms of your symbol energy and time duration, then we can write it PS equal to what? E by T. So it is symbol energy and this is your symbol duration. It could be T or it could be TS. Now moving towards the generation of your QPSK. So in generation of your QPSK, it is of two types. First is your OQPSK, that is also called as offset QPSK, or it is also called as staggered QPSK. I will tell why we are going to tell it offset QPSK. And second type of generation that we would see, it is what? Definitely non-offset QPSK. So let's start with this offset QPSK. Now you can see from this figure that this digital data, or this, it is in the form of your what? Bipolar NRZ signal. But suppose the input binary sequence, it is in the form of your 1 0. Then we have to first convert this binary sequence into what? Bipolar NRZ signal. Say it is of, we can say it is a digital data, or B of T. So that could be +1, which is for logic 1 input, and it could be -1 for binary input, which is equal to 0. Now over here, this block, it is nothing but your 2-bit serial to parallel converter. So this serial to parallel converter, it is nothing but your what? Demultiplexer. Now it is going to divide your B of T into two separate bit streams, as you can see, which is named as BO of T and BE of T. O, it represents odd bit streams, and E, it is going to represent even bit streams. So the bit stream B of ET, it consists of only even number of bits, that is 2, 4, 6, 8, like that one. So all the even number of bits, it is going to this multiplier over here. And similarly, the bit BOT, that is the odd bit, it consists of what? Odd bits. It means 1, 3, 5 or 7, as like that. So you can see over here, this is called a delay block. It is there. You can see it is what? Delay block it is there, which is going to be denoted by TB. It means each bit in the odd bit, it is going to be delayed by a duration of what? TB only. So after that one, there are two multipliers, multiplier 1 and multiplier 2. Over here, your local oscillator, it is there, which is going to generate your carrier, which is nothing but your root PS cos omega CT. And since it is a phase shifter, so it is going to change the phase shift of cos. So when the phase shift of cos it is going to take place, it would become what? Sine of omega CT. So this is a multiplier second. So you can see that the output of this multiplier and output of this multiplier, it is nothing but your BPSK, BPSK1, and this is BPSK2. So these two signals, BPSK signals, are added together to form what? QPSK output. So hope you understood this modulator. And since this delay is called a offset, so that's why it is called as what? Offset modulator, or it is also represented by your OQPSK. Now we would get the clear idea when we will see this waveform. But before that, just see this equation. It is also one of the most important equation VQPSK, it is going to be represented by C. It is root PS cos omega CT into B of ET. This is E of T. Plus, we are going to add it over here. What we are going to add? We are going to add root PS sine omega CT into B of OT. So, this is the equation, also one of the equation of your QPSK signal. So, please note down this equation also. This is what your QPSK output. Now from this waveform, if you can observe it, this is your input bit streams, that is 0, 1, 1, 0, 1, like this one. So we have considered this one. Now this input data 0, 1, 1, 0, 1, 0, they are converted into what? Bipolar non-return to 0, that is NRZ signal. It means 0 is going to be represented by -1, whereas logic 1, it is going to be represented by what? +1. Now, as you know that this is 1, 3, 5, 7, these are what? Odd bit streams. And this is even number of bit streams, 2, 4, 6, and 8. So we have categorized these bit streams. Now, the duration of each bit, it is of duration of what? TB. But you can see from this diagram that we have separate this B of T into two streams, as it is odd number bit sequence B of OT and even number bit sequence, that is B of ET. So you can see that each bit in the odd as well as in the even bit stream, it is going to be held for what? Period of 2 TB seconds. Remember, each duration it is of what? TB. And in each bit in this sequence, they are going to be held for what? Twice of TB. This plus this. So it means this duration is known as what? Symbol duration. That is TS. That is, every symbol it is going to contain how many bits? It is going to contain 2 bits. Now, as shown in this figure, you can see the first bit, the first odd bit, it would occur before the first even bit. First even bit, it is what? 1. But it is going to be occurred by a delay of what? TB duration, which is nothing but your offset. So first bit, that is the first odd bit, it is going to be occur before this first even number of bit. Hence, the even bit stream, this is your even bit stream, it is going to start with a delay of this 1 bit period after this first odd bit period. So this delay is equal to, as we know, it is of duration TB. This is called as offset. Hence, we call it as what? OQPSK, that is offset QPSK. Now, due to this offset, now what is going to be happen? Due to this offset, the bit stream B of OT and B of ET, they can't change their levels, you can see from the diagrams, at the same instant of time. So the bit stream B of ET, that could be +1 or that could be -1, which is superimposed on this carrier, that is root PS cos omega CT. And the odd number bit sequence, that is B of OT, which is also a +1 or it could be -1, it is superimposed on a carrier root PS sine omega CT. So by using what? 2 multipliers, as we have seen in the block diagram. See, this is your 2 multipliers are there, root PS cos omega t and root PS sine omega CT. And these are the what? Odd and even number of bits. So we have superimposed onto this carrier wave. So after that, what is going to be happen? they are going to generate a two signals, that is S of ET and S of OT. So over here we can say it is S of ET and it is S of OT. So these two signals are basically what? BPSK signal. You can see that how the phase shift it is going to occur at this transition. Similarly, at this transition phase shift it is there, at this transition phase shift it is there. So it is called as what? S of ET, which is nothing but B of ET root PS cos omega CT. This is your first BPSK signal. Similarly, this is the output of your second multiplier. You can see it that this is the transition taken place. So there is a phase shift, and directly now this over here the transition has been occurred at this instant. The phase shift it is going to occur at this instant. So we can write it S of OT is equal to what? B of OT into root PS sine omega CT. So this is another BPSK signal. So these two signals are added at this adder to generate your QPSK output. And this QPSK output, it could be represented by this equation. So hope you understood what? Offset QPSK modulator. Now we are going to see non-offset QPSK modulator. So this is your non-offset QPSK modulator. Now why the name it has been told put non-offset? So you can see from the figure this diagram and the diagram for the offset QPSK it is almost same, leaving one difference, that is of block delay. So over here no delay block it is there. So that's why, since no delay, it means no offset. So if there is no offset it is there, so that's why the name we kept it as what? Non-offset QPSK modulator. Again, the principal working of this both the modulator, it is one and same. Understood? It is your bipolar NRZ data, that is +1 -1. +1 it is going to represent logic 1 and -1 it is going to represent logic 0. So this is your demultiplexer, which is also called as 2-bit serial to parallel converter. Over here the even bits, that is 2, 4, 6 and 8 bit streams are separated out and given to this multiplier 1. Similarly, this is your odd number of bits, that is 1, 3, 5 and 7, etc. These are going to be added to separated and given to this second multiplier. So you can see again there is a carrier, that is a local carrier, same root PS cos omega CT given to the first multiplier. So output of this multiplier it is your what? S of ET, that is first BPSK signal. Similarly, second multiplier you can see there is a phase shift in the carrier, so it became what? Sine of omega CT. Due to this phase shift, this cos became sine. So output of this multiplier, second multiplier, it would be what? B of OT into root PS sine omega CT. That is, it is of what? Second BPSK signal. So these two BPSK signal added at the adder, and you would get what? QPSK output. Now, in offset QPSK as well as non-offset QPSK, simply we can also call it as a QPSK. Getting, guys? Non-offset QPSK, it is also called as just QPSK. So in both the QPSK, there is a brief variations in the amplitude of your transmitted waveform. And these variation, it is going to be take place because of what? This B of OT and B of ET. When there is a change of this what? Phase of the transmitted signal. But the amplitude changes are, more pronounced or more, we can say that observable in what? In this non-offset QPSK. Why? Because over here, since there is a no delay block it is there, so B of ET and B of OT can change simultaneously or at a particular instant of time. They can change simultaneously. So both these signals, it could be zero simultaneously and the signal amplitude may be reduced to zero temporarily. So due to this, what is going to be happen? There is a large amplitude variations are observed for this QPSK signal, because guys, in non-offset QPSK, the maximum phase shift is occurred, it is of what, 180 degree, whereas in QPSK, in offset QPSK, the maximum phase shift it is of what, 90 degree. But over here the phase shift it is large, that is of 180 degree. So these amplitude variation, it can cause difficulties in your QPSK communication system, which employs what, repeaters also, because it is a long distance communication, so it may have repeaters also. And as we know, generally the repeaters operate what, non-linearly. So due to this non-linearity, the repeaters generally, the amplitude variations, it is going to result into generation of spectral components outside the range of what, main lobe. So this is going to uh, remove the effect of band limiting filter, which is going to cause what, interchannel interference. So this is the important feature of your non-offset QPSK. Now next, that QPSK modulator, as we came to know, it is a bit splitter, that is your uh, two multipliers with two local oscillators, and which is nothing but your 2-bit serial to parallel converter and summer circuit. At the modulator input, as I already explained you, that message signals even bits, that is second, fourth, sixth, and odd bits, that is first, third, and fifth bits, are separated by this bit splitter or demultiplexer. And then they are going to be multiplied with the same carrier to generate your odd BPSK and even BPSK. After that, this PSK, that is your even BPSK signal, is phase shifted by 90 degree before your modulation. This is the waveform of your QPSK. You can see it, that see 4 symbols are there, and how the phase variation it is going to occur differently at the different transitions, that 00 to 10, 10 to 01, and 01 to 11, how the transition it is going to take place. Now this is your QPSK demodulator. So as you can see from this diagram, that QPSK demodulator, basically it consists of your multiplier 1 and 2 with band pass filter 1 and 2, and this is your integrator low pass filter 1 and integrator 2. Similarly over here, local carrier oscillator it is going to there. Input, it is nothing but your output of your modulator, that is QPSK input, and the output of these two integrators are given to this 2-bit parallel to serial converter, that is, it is your multiplexer, and the output it is your original data. So QPSK demodulator, it is uses what, two product demodulator circuit with local oscillator, 2 band pass filter, 2 integrator circuit, and 2-bit parallel to serial converter. The two product detectors at the input of demodulator, simultaneously they are going to demodulate the two BPSK signal, and the pair of bits are recovered here from the original data, and these signals after processing are passed to the what, parallel to serial converter. After seeing the detection of your QPSK, now we are going to see the signal space, that is geometrical representation of your QPSK. So as we know this equation, that VQPSK is equal to this root 2 PS cos omega CT plus 2m plus 1 pi by 4. Now if you are going to put this m, different value of m, you are going to get a different carrier wave over here with a phase shift of multiple of this pi by 4. So now let us expand this equation by using a standard trigonometric rule that we know cos of a plus b is equal to cos a into cos b minus sin a into sin b. So let's use this trigonometric standard to this cos of, say this a is nothing but your omega ct and b it is nothing but your 2m plus 1 pi by 4. So applying this, you can get the equation like cos omega ct into cos 2m plus 1 pi by 4 minus sine of a, that is sine of omega ct into sine of 2m plus 1 pi by 4. Make it as equation number 2. Please, according to this, you also write this one simultaneously so you can get the idea of signal space representation, because I couldn't move backward. So at the same time, you also write the equation. Now moving further, we can rearrange this equation. See, we have rearranged this equation number 2 as what? We have introduced this term that is Ts and Ts. We have what we have done, that we have put Ts into the square root. So we can write it square root of Ps into Ts, that is cos of 2m plus 1 pi by 4 into square root of 2 by Ts cos omega ct minus, similarly you can write it root of square root of Ps into Ts sine of 2m plus 1 pi by 4 into square root of 2 by Ts sine omega ct and make it as equation number 3. Now, after rearranging this equation, observe this equation carefully. So let assume that root 2 cos 2m plus 1 pi by 4 root 2 cos of 2m plus 1 pi by 4, it is represented by what? B of et, that is even bit stream. And similarly B of ot, it is nothing but your root 2 sine of 2m plus 1 pi by 4, make this as 4. So over here it is a even bit stream and over here it is a odd bit stream. Similarly, phi 1 of t, phi 1 of t, it is square root of 2 by t s cos omega ct. Phi of 1t or u of 1t, it is one and same because we are going to take u1 of t for representation. And similarly, phi of 2, or we can also call it as a u of 2t, it is nothing but your square root of 2 by ts sine omega ct, make it as 5th. Now substituting this equation 4 and 5 into equation number 3, what you would get it now? So you would get it root PSTS 1 by root 2 B of ET and into U of 1T plus, that is square root of PSTS 1 by root 2 B of OT U of 2T, make it as equation number 6. Now from this equation number 6, Ts is nothing but your symbol duration, and in QPSK 2 successive bits it is going to form one symbol, and hence Ts is equal to what? Twice of 2b. So put Ts is equal to twice of 2b in equation number 6. So your equation 6, it would become 2Ps Tb 1 by square root 2 B of Et U of 1 of t plus 2Ps Tb 1 by root 2 B of Ot and U 2 of t, make it as equation number 7. Now as we know that Ps into Tb, it is nothing but your energy per bit. So you can put it, and if you are going to put PSTB is equal to E naught or EB in equation 7, say EB, so the equation, it would become what? Square root of EB, B1 of t, then plus EB, B of OT plus U2 of t, make it as equation number 8. This root 2 get cancel. This equation we are going to use to plot your signal space representation of your QPSK signal. And remember, U1 of t and U2 of t are nothing but your reference axis. So now see this one. This is your signal space representation of your QPSK. This is your U1 of t and this is your U2 of t. As we know, U1 of t is equal to square root of 2 by ts cos omega ct, and U2 of t, it is square root of 2 by ts sin omega ct. This is the symbol S1, which is nothing but your 0, 1. So 0, it means odd number bit stream, it is a -1, and even number of bit, it is what? 1. Similarly, symbol 2, that is equal to 00. Since both are 0, so odd number bit stream and this even number bit stream represented by -1. Similarly, symbol S3, which is nothing but your 10. As we know, 1, it is your odd bit. So it is 1, so it is going to be represented B of it equal to 1. And since it is a 0, so B of ET, even number, it is represented by -1. And last, S4, both are 1. So odd number and your even number bit streams are represented by logic 1. You can see this, the difference, between these 2 points. The 2 points, it means they are going to be differ only by 1 bit. So this distance is nothing but your twice of root of PSTB. See, this is what? Root of PSTB. This is also root of PSTB. So addition of this, it would be what? Twice of PSTB. So it would be twice of EB. Understood? And this is your origin. And the distance of any point from this origin, you can calculate it. And by calculating, you would get what? Square root of ES. That is nothing but your energy per bit. So this is your signal space representation or geometrical representation of your QPSK. So you can write the conclusion from it, and you can see over here the phase angle, it is a pi by 4, 3 pi by 4, then 5 pi by 4 and 7 pi by 4. So what conclusion you can write it from over here? So from this, you have to find the distance, and 0 to S4, this is the distance. Now we are going to find it. So you can find this distance, that 0 to S4 square is equal to what? Square root of PSTB square plus square root of this PSTB whole square. So you make it as equation number 9. You can write this by omitting this square root, and since it is a square value, get cancel, and you would get PSTB plus PSTB. So you can write it as twice of EB, because PS into TB is nothing but your energy per bit, twice of EB. Or simply you can write it as what? ES, that is a symbol energy, make it as equation 10. Hence distance 0 to S4, origin to S4, it would be what? Since square, so we need to find or omit this square term, we would get the square root of this ES. So the distance of any point, so what? Make it as equation 11. So you can conclude that all the signal points, that is S1 of t to S4 of t, are at an equidistance, that is of square root of ES from the origin. This is our first conclusion. Second conclusion, you can find it, as I already told, the difference between or the distance between the points which differ in a single bit is given by this formula, that is D, that is equal to twice of PSTB. It means twice of root of EB. So this is your second conclusion, make it as equation number 12. And third conclusion is that the distance D for QPSK is, exactly same as that of your BPSK system. This distance D, it is nothing but your Euclidean distance, which is same, and hence the noise immunity of the QPSK system is exactly same as that of your what? BPSK system. So while explaining your signal space diagram or representation of your QPSK, you can write this conclusion. Now moving towards the next part, that is the spectrum of QPSK. Now we know the power spectral density of NRZ bipolar signal with a period TB is represented by this equation. S of F is nothing but your power spectral density. PSTB sine of pi FTB upon pi FTB whole square. This sine of theta by theta is nothing but your sinc function. So in QPSK signal, this signal B of t is divided into what? Even and odd bit streams. That is B of ET and B of OT respectively. So each symbol in these bit streams has a period of what? Ts. Hence, the power spectral densities in this even stream and odd bit stream, it is given by this equation. SEF, it is nothing but your power spectral density of your even bit stream. So make it as equation number 14. TB is replaced by TS because it has a period of TS symbol duration. Similarly, this is the power spectral density of your odd bit stream. Make it as equation number 15. Now, by adding this equation 14 and 15, what you would get it? You would get what? The power spectral density of your QPSK. It would be addition of this even and odd. It means S of EF plus S of OF. It would become what? Twice of PSTB sine of pi FTS upon pi FTS whole square. Make it as equation number 16. So this is one of the most important equation for drawing your spectrum of QPSK signal. So from this equation, you can see that how the spectrum it is going to look. As we know that this is your PSD of your baseband QPSK signal. See, you can see it from here. And as we know, the PSD of the QPSK, it is divided into even and odd bit stream. So we have seen the two equations. And this is going to tell you that this is centered, the spectrum components, it is centered at plus C, FC and minus FC. So this is your main lobe, all the information present in this main lobe, and bandwidth is given by what? FB, that is FC plus FB2, FC minus FB2. So the difference between these 2 points, it is going to give you the bandwidth that is of FB. And similarly, this is another spectral component which is also has a bandwidth of what? FB. So you can see that bandwidth of your QPSK system, it is what? Half of your bandwidth of BPSK signal. Because in BPSK, what was the bandwidth? It was twice of FB. But over here it is what? FB. So this is the advantage of your multi-level modulation, that is a reduction in the bandwidth it is there. So bandwidth requirement it is less. It is just what? FB. So as I already told that bandwidth it is what? Twice of FB by 2, that is it is of only FB. Now the error probability of QPSK system, it is given by the same formula, that is of BPSK equation. So the performance of your QPSK in presence of noise, it is equivalent to your BPSK system. Now what are the advantages of QPSK system? Very good noise immunity as like of your BPSK, low error probability it is there, and as we have seen that baud rate is half the bit rate, therefore more effective utilization of the available bandwidth of the transmission channel. Next, what is the drawback? The generation and the detection of QPSK is quite complex. Now, why QPSK is better than your BPSK? Now, due to multi-level modulation used in QPSK, there are 4 symbols are there. It is possible to increase the bit rate to the double and then that of your BPSK without increasing the bandwidth. So the noise immunity is same as that of your PSK system. The noise immunity is same as that of your PSK system, and available channel is utilized in a better way by the QPSK system. Now we can see the comparison of your BPSK and QPSK. First variable parameter, it is your variable characteristic. Now as we know in BPSK and QPSK, the same variable characteristic of carrier, it is what? Phase. Then what is the type of modulation? Since it is a 2 level, that is a binary 0 and 1, but over here the modulation it is of 4 level. Types of representation. A binary bit is represented by one phase state, whereas in this one a group of 2 binary bits is represented by one phase state. Bit rate is equal to baud rate in BPSK system, whereas bit rate is twice of your baud rate in your QPSK system. Detection method is both coherent and complexity. BPSK is complex, but QPSK is very complex. Applications, BPSK it is used in high bit rate and QPSK it is used in very high bit rate. So today we have seen that why QPSK, how we have represented QPSK, then we have seen the generation of QPSK, that is offset and non-offset QPSK. Then we have seen the detection of your QPSK, how we are going to represent geometrical representation of your QPSK, power spectrum, what are its advantages, drawbacks, and at the last we have seen the comparison of your QPSK with your BPSK. This is the assignment, so please take this assignment, note it down. In next module, we are going to discuss about your DPSK, that is differential phase shift keying. This is my email address. It's all about our today's lecture. Thank you very much.